last video here talking about dimensional analysis. Want to give you a heads up if you did not watch the last video that I am having to do the math in Google Docs, unfortunately, and so it's going to look a little bit different. If you have any questions, please swing by and we can do it on paper, but this should still hopefully help as I can show a lot of the math. I can show all the math, it's just a little bit, looks a little bit different because I can't get to my superscripts or write it with my hands writing, which is just a little bit easier, but let's get going. So dimensional analysis, as we talked about Monday, anytime we're doing dimensional analysis, whether we're doing that first version, the normal kind that we did in Unit 1, or the mole-based dimensional analysis, first step is always to find your conversion factors. So here, if we read number 1, how many inches are in 80 meters? Remember that 2.54 centimeters is an inch. Oh, there we go, we just hit one, right? 2.54 centimeters is an inch. That means that this 2.54 centimeters equals 1 inch. So we're going to want to write that off to the side. So as you can see, wrote that one off to the side, great. And that 1 meter is 100 centimeters. So I'm going to write that to the side as well, because this is saying 1 meter is 100 centimeters. 1 meter is 100 centimeters. So first step in these problems is always just get those conversion factors written off to the side. It helps organize your brain, helps you get going. And it also does something in that it helps us know that these aren't the things I'm starting with. These are going to go in the table, but they are not what I'm starting with. What I'm starting with is going to come from the question itself. When you read the question, how many inches are in 80 meters? Then what you want to pick up is what units you're going between. So we are going between inches and meters. 80 meters. All right, that means that meters, that is 80 meters is what we're starting with. What I always do is I look for my units, right? And then whichever one of them has the number, that's what we're starting with. So inches, well, there's no number with inches. There is that number with meters. This is where we're starting. So I start my table with 80 meters in the top left, remembering that this is a fraction, and so it's really just being over 1, but we frequently don't write the 1. If you'd like to, you can. But we're starting with 80 meters, and we're going to go down this line where we are multiplying by these conversion factors set up so that the units cancel out. So I'm going to put 1 meter here on the bottom so that meters will cancel out, because just like with a variable, units can be set up to cancel out as well. So 80 meters here, starting out, multiplied by 100 centimeters per meter. The meters will cancel out, and at this point we're in centimeters. Well, the problem wants me to go to inches, so I'm not quite done yet. I'm going to put 2.54 centimeters there on the bottom and 1 inch on the top, because this is the other conversion factor pulled from right here. 2.54 centimeters is going on the bottom, 1 inch is going on the top. Centimeters cancel out, and I will quickly kind of show that. Meters are gone, centimeters are gone. The unit that we are ending in at this point is inches, and that's what we wanted to get to. So we are set up and good to go. The last step is doing the calculation itself. This is a fraction, just a slightly different stylistic way of writing a fraction, multiplying by fractions. So everything on top multiplies. 80 times 100 times 1. Everything up top multiplies. So 80 times 100 times 1 equals 8,000. Great. Everything on bottom also multiplies. So 1 times 2.54, because we want to get that kind of total for the bottom. And then we take the top, which was 8,000. We divide it by the bottom, which was 2.54. And we find that 3,149.6 inches are in 80 meters. Great, let's look at another example here. The current exchange rate for money between the US and Canada is that 0.74 US dollars is equal to 1 Canadian dollar. Oh, wait a minute, equals, okay, that's a conversion factor, right? So again, first step, I'm going to write that conversion factor on the side. It's going to help me kind of organize my thoughts and get going on the problem. All right, you have 40 US dollars. Okay, well, this one's not equal to anything. Yeah, think about that and move on a little bit here. Move past the conjunction. A dish of poutine costs 13 Canadian dollars. Ooh, this is another kind of sneakier conversion factor. Is 1, right? So 1 dish equals $13, Canadian dollars in particular. So I'm going to write that one off to the side. Okay, still not sure about that 40 US dollars. A little bit of a puzzle. Let's give it a minute. Let's see if there's anything else that's a pretty significant conversion factor that we can find. Nope. We are at the end of a problem. So first step, write all your conversion factors aside, done. Second step, try the problem, find that problem, and figure out what units you're going between. So here, how many dishes of poutine can you buy with the money you have? All right, we are going between dishes of poutine. Okay, so that's one quote-unquote unit. And the other is the money you have, right? So how much money do I have? Well, that number finally showed up, right? I have 40 US dollars. That's what I'm starting with. So I put 40 US dollars here in the first bit. And then my goal is to get the US dollars to cancel out. So I'm going to put 0.74 US dollars makes 1 Canadian dollar. Brilliant. Well, now I need to get rid of Canadian dollars. So I'm going to use the next conversion factor, put 13 Canadian dollars on the bottom, and 1 dish of poutine on the top. US dollars canceled, Canadian dollars canceled. Now we're in dishes of poutine. So again, everything on top multiplies across, 40 times 1 times 1. Everything on bottom multiplies across, 0.74 times 13. And you do the top, do the bottom, and then divide the top by the bottom. What you're going to find is that you can buy about 4 dishes of poutine. Seems like a good amount of poutine. All right, we're going to move on down here to this other type of dimensional analysis. The really nice thing about the mole is that there are only 3 conversion factors that we ever use. So whenever that first step of finding the conversion factors, you know which ones you're going to be using every time. So these are the 3. And all 3, you will notice, are equal to the same thing. They're all equal to 1 mole, all right? So what I really encourage people to do is focus on these units, right? Which are grams, molecules, and liters, because that's going to help us figure out which one we're using. So here, what conversion factor do we use to convert between grams and moles? If you look at your option of 3, which one has grams? Oh, this one, right? So we're going to be using molar mass. Molar mass we did with percent composition and here. Molar mass comes from the periodic table. You're going to look at the periodic table and you're going to see if you can find the correct element. You're going to find the correct element, and then you're going to look at the molecule, see how many of that element you have, how many atoms of that element you have in the molecule. You're going to add up those masses, and that is what molar mass is, right? So let's go ahead and solve 2 and 3 here. Let me pull up the periodic table. Alright, so whenever we're doing these problems that have the mole in them, it's pretty likely we'll need that periodic table. So pulled it over so we can use it. Let's look at this first problem. So step 1, we want to find all of the conversion factors. We've got them here on the side. Great. Step 2, read the question and figure out what units we're going between. Well, it looks like we're going between grams and moles on this one. Which one has the number with it? Well, 345 grams. So we're going to be starting here with 345 grams. That means that I know that the unit that is going here is grams. I do not know the number yet because that's the molar mass, and I'm going to have to go to the periodic table to find that. But I know that the unit of grams has to go here because the same principle of everything else. So the molar mass in grams of gold is going right here. Right? Well, let's look at this next problem just to kind of do 2 things at once here. How many moles are in 180 grams of sodium fluoride? Well, same thing. I've got my conversion factors ready to go. I need to see what I'm going between. This one I'm going 180 grams to moles. So I'm going to put 180 grams of NaF. I should have put gold up here. And I know that this is going to be the molar mass of sodium fluoride, and above it would be 1 mole. So When we're doing these are, one-step dimensional analysis problems. The thing that folks get tied up on is how to calculate that molar mass. Luckily, you've done it a couple times, well, more than a couple times, so hopefully you remember, and this looks familiar as we come across the periodic table. So, on the periodic table, those precious metals, copper, silver, gold, are all in a row right here. And if I look, there's my upper right number, 197 is the mass of gold. That's the atomic mass of gold, and in this case, since it's just the one atom, that's it. I put 197 in here. I take 345, I divide it by 197, and that's it. If you want me to write the 1, I can write the 1 up top, 345 times 1. Down low, we just have 197. So doing that will tell you how many moles of gold you have in 345 grams of gold. All right? Similarly, here, 180 grams of sodium fluoride. Well, sodium fluoride is not one atom. We can see big letter, little letter, this is one atom, sodium, and this is another type of atom, specifically fluorine. And so for this one, we're going to have to add the masses together. Remember when we looked at percent composition down here in the previous video, it talked about how for molar mass, right, we find the mass from the periodic table, we multiply by however many there are, that gives us the total mass of that element, we add them up and get the molar mass. Same thing here. To find the molar mass in grams for sodium fluoride, I go to the periodic table, sodium is over here. I'm going to go ahead and round that mass up to 23, so that's about 23, and fluorine over here, opposite side, is about 19. I have one of each of those atoms, as indicated by the fact that there's no number written as a subscript. So 23 plus 19 is going to give us 42 grams for sodium fluoride. 42 grams of sodium fluoride is 1 mole of sodium fluoride. Great. 180 times 1 divided by 42 is going to tell us how many moles. All these problems that are just going moles to grams are one-step dimensional analysis problems, and we're using this conversion factor, and it just requires that we know how to find molar mass. So that's the part that is hard for folks. If we move on and look at molecules to moles and back again, these are also one-step dimensional analysis problems, and we are still using the same conversion factors as before, these three. Okay, we're going moles to molecules. Which one are we going to be using? We're going to be using this one up here at the top, right? Because this has the unit of molecules, so this is the one that we want to be using. So if we look at this first problem, so number 1, we're using Avogadro's number, which is 6 times 10 to the 23rd molecules, which is that first option on the list. How many molecules of water are in 5 moles of water? Well, 5 moles of water. Great, if I look at the conversion factor, I'll see 1 mole is 6 times 10 to the 23rd molecules. I had to write the 23 power like this because I couldn't get the superscript to work. And so I put 1 mole here so that the mole unit cancels out. And I would put 6 times 10 to the 23rd molecules on top. Just like before, 5 times 6 times 10 to the 23rd is going to give us our answer divided by 1. Remember, this is why we talk about scientific notation in chemistry, is because we're so frequently dealing with that very, very large number. I'm going to go ahead and do one last little thing here showing how to set up a multi-step mole dimensional analysis problem. So on this problem, I'm using the same 3 conversion factors right here. Read the problem, and it says how many molecules in 1.3 grams of phosphoric acid, so I know I'm starting with 1.3 grams. I'm going to need the molar mass to cancel out to get to moles. I can then use Avogadro's number, 6 times 10 to the 23rd, to get to molecules. When I add up the mass of all the atoms in phosphoric acid, I get the mass of 97.994. Everything from this point on is as normal. That wraps up the video, y'all. Hope it's helpful.